Hi, this is an example problem about diffraction gratings from chapter 27. Pause for a moment to read the question. All right, so we are dealing with the diffraction grating here. This is very similar, you can see a picture of it, to the double slit interference apparatus. This is essentially similar to that, but it just has a lot more slits. In reality, the slits here are really close together. There's tons and tons of these little slits, and it's a small area, so this is not to scale. That screen is much bigger. The picture above kind of shows you more what it looks like. The effect of the diffraction grating is to go ahead and produce maxima that are spaced out away from the central maximum. In this question, we're asked, find the angle at which one would observe the first order maxima. So if we go and look at the equations for diffraction gratings, we see that it has the same form as the equation for the double slit, as I was saying before. And we're only interested in the bright ones because the diffraction grating is to separate out light so that you can see the bright spots. For that reason also, we don't usually look at m equals 0, which doesn't separate the light. All colors get sent to the central bright spot. So we're going to look at m equals 1 in this case, the first maxima beyond the central maximum. So in our problem, let's go ahead and write down this equation here. The important thing when you're doing diffraction gratings is to figure out what d is equal to here. They usually don't tell you what d is. Instead, they told us this. They said that the number of lines per centimeter is 6,000. So really, like if we had 1 centimeter of length here, we would have 6,000 little slits here. That's what that means. Now, to get the length between two adjacent slits, what is this length here? That is your d. We have to take the reciprocal of the number. So d in this case, it's going to be equal to 1 divided by 6,000 lines per centimeter. And that comes out to 1.67 times 10 to the minus 4th centimeters between adjacent lines. Now we can go ahead and use this to figure out what the angle is here. So using the equation, let's go ahead and write this as sine theta. We're going to do bright 1 is equal to m lambda over d. We want to calculate what the angle is, so theta b1 is equal to sine inverse. In this case, m equals 1, lambda 632.8 nanometers, which I'm going to convert to meters, all divided by d. Well, d is given in centimeters. We need to convert that to meters. Well, we can do it like this. Just like we did with nanometers is 10 to the 9th meters. Well, centimeters is equal to 10 to the minus 2nd meters. And so altogether, this is going to give us 1.67 times 10. I add those, right? So minus 6 meters. And plugging that into the calculator, we get 22.3 degrees. And we canceled our meters out, so that gives us confidence there. All right, for part B, it asks us, what is the highest order maximum that can be obtained with this grating at this wavelength, right? So we just found out that, our m equals 1 here, that one is going to be at an angle of 22.3 degrees. And, we can go ahead and draw some more of these, right? Maybe we have another one here, m equals 2, right? How far can we keep going until we're going to go beyond 90, same as we saw before. We can't go beyond 90, so we're going to go ahead and set the angle to 90 when we're calculating what the m value will be. Let me just move this around a little bit here. So this was part A. Now we're looking at part B. And for part B, we're going to use the exact same equation here. So if we're looking at, again, for part B, sine, we're going to use 90 degrees now. And that means that the m lambda is going to have to be less than or equal to that 90 degrees. And that's going to give us our maximum m value. So we just need to solve for m now. So what we're saying here is we've got 1 less than or equal to m lambda over d. We're going to go ahead and multiply by d over lambda on both sides. Canceling these out and leaving us with m. And if we just turn this equation around here, we're going to find out that m has to be less than or equal to d divided by lambda. And so in this case, we know what our d value is. It is 1.67 times 10 to the minus 6th meters divided by the wavelength, which is 632.8 times 10 to the minus 9th meters. Now our meters cancel, and we're going to get a value of m less than or equal to, gives us a 2.64. And again, careful, don't round up. We always got to round down. M has got to be less than that. So m in this case, the maximum value is going to be equal to m equals 2. So there won't be anything beyond the m equals 2 one that we see here. We're only going to have 2 bright interference spots, plus the central maxima that are coming off there. Of course, you've got 2 bright ones, m equals 1, m equals 2, below the central maxima as well.